Hello and welcome to helpyourmath.com. In this video, we're going to look at an introduction to relations and functions. First, we're going to start with relations. So in mathematics, a relation is a relationship between two sets of values. These sets of values are called the input values and the output values, or they might be called the domain and range. The domain refers to the set of input values, and the range refers to the set of output values. So we have domain and we have range output. The input values are the values that get plugged into the relation, and the input values are the ones that make up the domain. The output values are the values that are generated as a result of the relation, and the output values make up the range. So again, we can use these interchangeably: input domain, output range. Also, very frequently, the variable x represents any input values of the relation, and we use y to represent any output values. Again, that's just the most common, but it's not necessarily set in stone. There could be other variables, there could be no variables. Somebody could get fancy and switch them for some reason, but very commonly x refers to the input or the domain values, y refers to the output or the range values. And we say an input value maps to an output value. So when we're talking about the relationship, one word we might use to describe it is mapping to. And that brings us to different ways that we can express relations in mathematics, the first one of which is called a mapping. So with the mapping, we have two ovals and we have arrows connecting the input to the output. So we see here -3 is mapping to -4. 6 maps to -2 and 1/17. 7 3/4 maps to -5, and 10 maps to -4. Frequently, these ovals are labeled, which I failed to do. They can either be called input-output, so we would have the input oval and the output oval, or we could have domain and range, or if they really wanted to get lazy, they could just put a D over the first oval and an R over the second to indicate domain and range. When we write the domain and range, it might ask you, so it might say, okay, great, we have this relation, but now write the domain and write the values in the range. And what we would want to do is we would say domain, and then we would, open up a set of braces. Braces are like the fancy brackets. And when we list them in order from least to greatest. So luckily for us with the mapping, they already are in order from least to greatest. We have -3, 6, 7 3/4, and 10. And then we do the same thing for the range. So the range, we would open up a set of braces and we would go from least to greatest, which again, with the mapping, we already have that, -5, -4, -2, and 1/17. Now it's important to note, and it's pretty obvious with the mapping, but we only write each unique value once. So even though there were two numbers that mapped to -4, we had -3 mapping to -4 and 10 mapping to -4, we only write -4 once. The domain and the range, we only include unique values once. And so that's the point I make there. And then typically values are listed in order from least to greatest. So with domain and range, unique values once in order from least to greatest. Another way we can show a relation is a list of ordered pairs. So we see here we have 4 ordered pairs, and it might say, okay, list the domain and range. We would say the domain, so we only put unique values of the domain, and we have 4. We're not going to write the second 4 because we already have 1 4 in our domain. And the domain here, it's going to be the x value. So each of these are an ordered pair. That would be xy, this would be xy, this would be xy, and this would be xy. So all x values are part of the domain. That would be 4, 8, and 19. And then the range values will be those 4 y values. And let's see, the smallest of which is -1. Then we have 0.5, 3, and 8. So we only put each unique value once when we write the domain and the range. Both of these were examples. So we saw the mapping and we saw this list of ordered pairs. These would be relations with a finite number of values in the input and a finite number of values in the output, just meaning we can count. So there are 1, 2, 3 values in the domain, and there are 1, 2, 3, 4 values in the range. If something had an infinite number, it would be a lot harder to list. We might have to use set notation or something else to help us list the domain and range. Another example of a finite relation would be a table. So we can express input, output, and again, you might also see domain and range at the top of the table. It just depends who's writing it. Whoever's in charge gets to decide if they want to call it input, output, or domain and range. So again, we see here our list of inputs and our list of outputs. So if we wanted to write out, if it asks us, we could write the domain. We go in order from least to greatest, which the x values already do, 12 and 17. And the range, so let's see, -10 is the smallest, then we have -4, and then we have 3. And again, even though we see a bunch of -4s, we only put it one time when we list the range. It just gets listed once. Another common way to show a relation is through a graph. And so just so we see, because every example we've seen thus far has been when there's been a finite number of values. And here in this graph, we see a finite number of values again, but the second graph I have does have an infinite number of values. So for this one, what might be easier for the domain is to actually write the ordered pairs out. You can do this just on the graph, or you can do it on a separate sheet of paper, whatever makes the most sense. So this is -7, -2, and again, this would be x, and this would be y. Here we have -6, 0, that's x, y. -2, -1, xy. 1, 1 would be xy. Down here we have 1, -4, xy. And then here we have 4, 0, xy. So if we were to list the domain and range for this graph, we would get to use the braces. So the braces do indicate that we do have a finite number of values. If we had an infinite, we would have to use parentheses and or brackets. And we have -7, -6, -2, 1, and 4. I see the 1 repeats, but again, we put each one time. And the range here, so we would go to the bottom, there's -4, -2, -1, 0, and 1. I see there's 2 zeros, but again, we only put it one time. Okay, finally, an example of an infinite number of values. So for this one, when we list the domain, we do have to use set theory, a set notation, which includes parentheses and brackets. Parentheses indicate that the endpoint is not part of the relation, and a bracket would indicate that it is. We know on the graph, when something's included, it's a closed circle. So at -8, I see that's a closed circle. But here at -2, that's called an open circle. That means that here, -2 is not included in the domain. However, -2 is right here because there's a closed circle here. So open circle just indicates that this point, -2, 0, is not actually part of this relation. Not part of relation. So we can just say that. And then if we have a closed circle, which we see for all the other ones have closed circles. A closed circle indicates that it is part of the relation. Part of relation. Okay, and again, this can get a little bit trickier when we're writing the domain and range, especially because this is such a fragmented graph. So really what we're looking for is the domain is going to be the x values. So the smallest x value I see is -8, and then it goes all the way up to -5. But then there is part of the graph down here, so it can get a little bit tricky because there's actually no break in the domain, even though there's a break in the graph. So it still is continuing at -5. It does continue at -2, even though here it's not included, and it goes all the way to 2. So the domain would extend from -8, and we use a bracket when it's a closed circle. That indicates that -8 is part of the domain, and it goes all the way to +2, and +2 is included because there is a closed circle. The range, let's see if there's anything weird with the range. So the range, the bottommost point of this is at -4. And then the graph goes up, it goes up, it goes up, it goes up. It stops here at 0, but it was also over here. So it continued here. And then let's see, it stops here, but it continues here. And the highest point here would be at 3. So the range here would be from -4 to +3. That one can be a little bit tricky, and there are more videos that go into more detail about these types of relations and functions, so you can watch those if needed. But the domain would be from -8 to 2, and the range would be from -4 to 3. And the last way that we can express a relation is through an equation. So equations, we might see something like y equals 3x minus 7, y equals the absolute value of 5x plus 11, y squared minus 4x squared equals 9, y plus 3x minus 20 equals 0. So we have two variables and there's something connecting those two variables. In this case, it's a relation. Okay, that brings us to functions. So what is a function? A function is a special type of relation. It's a relation in which every input maps to exactly one output. So what that means is that if 2 is an input value, 2 only maps to 5, or it only maps to -7, or it only maps to 0. It doesn't map to 5 and -7 and 0. So it only maps to exactly one output. So let's determine which relations we've discussed so far, which of these are functions. So first, our mapping. So -3 maps to exactly one value, so -3 is good. 6 maps to exactly one value. 7 3/4 maps to one value, and 10 maps to one value. So we would say, yes, this relation is a function, because each input maps to exactly one output. It's okay that 2 of them map to -4. That doesn't determine whether it's a function or not. Yes, that is a function. Next, we had the table, the list of ordered pairs. So in the list of ordered pairs, what we're looking for to see if it's a function are the input values or the x values. So x here is 4, x here is 4, x here is 8, and x here is 19. The fact that I repeated myself, I said x here is 4 twice, indicates to me that 4 maps to two different numbers. It maps to 3 and it maps to -1. This would not be a function. This is not a function because of the 4. In our table, if we look at our input values, we can clearly see that every input value is different from every other input value. So we would say, yes, this is a function. And in our first graph, you might recall that we listed the ordered pairs. And again, what we're concerned with to determine whether something's a function or not are the x values. Here, the x value is -7. Here, it's -6. Here, it's -2. Here, it's 1. Here, it's 1. And here, it's 4. Since I have 2 that both have an x value of 1, that indicates to me that 1 maps to two different values. It maps to 1 and it maps to -4. So this one was not a function. Okay, the last few, we had this other graph, and we can see here that we have a value at -5. We have a point right here, and at -5 we also have a point right here. So the fact that I can find a place where we have -5 mapping to two different values or something mapping to two different values indicates to us that it's not a function. Important to note, so this one's not a function because it didn't work at -5. It doesn't work right here, right? Because there's a point here and a point here. There's a point here and a point here at -6. If we had open circles and if they didn't overlap like that, like right here at -2, that wouldn't violate whether it was a function or not, because here at -2, it only maps to -2 once. The open circle indicates it didn't map a second time. So if we had a series like that, then it would be a function, but we don't, so it's not. Equations are the hardest, and so I'm going to go through these a little quickly. There is another video that you can watch if you want more detail about determining whether relations are functions. So please watch our video, the other video. But basically, the quick way to describe whether a relation is a function when we're given an equation is something annoying happening to y, and if it is, then it's probably not a function. Here we have y equals 3x minus 7. You might recognize this. It's a linear equation. Linear equations, unless they're vertical lines, will always be functions. So this one is a function, yes. Y equals the absolute value of 5x plus 11. Again, nothing annoying is necessarily happening to y. In fact, y is by itself. That's a pretty good indication that we are dealing with a function. Y squared minus 4x squared equals 9. Something weird is happening to y. Y is being squared. That's weird. That generally indicates not a function. And then here we have y plus 3x minus 20 equals 0. You might say, well, why not? Y isn't by itself, and doesn't it have to be by itself? Yeah, but we can get it by itself, and it won't be that bad. We would add 20 and subtract -3x. So it would give us y equals -3x plus 20, which is a linear equation that wasn't so bad to get y by itself. And yes, this is a function. So hopefully this was instructive video for relations and functions. And again, if you want more information about functions, watch the other videos. Thank you for stopping by.